Okay, so we were talking about homogeneous nucleation, right? And the important thing to remember is that this is exactly the same as solidification for the most part,
I was gonna
right?
say, have we gone back in time to homogeneous solidification or something?
It is. This is it. Nucleation in solids is exactly the same as solidification, right? As nucleating solid from liquid. The only crucial difference is we need to take account that solids, that there's a volume misfit, right? And whereas a liquid or a vapor can flow easily under the shear stress, right? Solids can't. They resist, right? They keep their shape. So we have to account for the volumetric strain, right? And that volumetric strain just reduces the driving force for the phase transformation, much like the surface energy reduces the driving force. And we need to account for that. But other than that, the theory is exactly the same. We have an activation hump that's given by delta G star. We have a minimum stable cluster size that's given by R star, right? Right? This is exactly the same. The only other difference is with the rate, right? Because what we have is we have a diffusion term. We have to consider the fact that atoms need to move. We don't have perfect mixing or fast diffusion like we had in a liquid. In the solid, we have a much slower diffusion. We have to take that into account. And so at high temperatures, we have a very small bulk free energy. So our Gibbs free, our G star is small. As we get to larger and larger undercoolings, our G star increases, right? And we have a larger and larger driving force for the transformation. But as our temperature drops, we have much less mobility, right? So this gives us a peak in our nucleation rate. There's very low nucleation up here because we have limited driving force. There's very low nucleation down here because we have limited mobility. But somewhere in the middle, there's this magical regime where we have a finite nucleation. Right? So those are the primary differences. Okay? And that's where we left off Monday. I want to point something out here, that the nucleation rate is going to be dependent on the composition, right? Right. Both in terms of the mobility and in the undercooling, right? If I'm at composition 1, for any given temperature, I have a larger undercooling, but my diffusivity is the same, essentially, right? So that means that the richer I am in supersaturation, when I come down into the two-phase region, the faster my nucleation is going to be. Right? Does that make sense? Right? It follows our intuition, right? That the greater my supersaturation for any given temperature, right? If I quench down from the single phase region into the two-phase region here, alloy 1 has a higher degree of supersaturation than alloy 2. It also has a larger degree of undercooling because of that. And therefore, we're going to have faster nucleation. Right? Okay, so that brings up an empirical rule for alloy design, right? Which is, if you want an alloy that has good precipitation hardening, right? You want a very sharply curved Solvis line, right? If this goes up just a little bit, it's very difficult for me to get these large supersaturations and large undercoolings necessary to get high nucleation rates, right? Right. We'll see this in aluminum in just a little bit, right? If I want a uniform dispersion of precipitates, I need easy nucleation. If I only have a little bit of nucleation, I'm going to have very few particles that are going to grow large. If I want lots of small particles, secondary phase particles, I need to enhance my nucleation, right? And so one of the key principles in designing alloys, and if you take the physical metallurgy class next year, you'll see this in spades. You're trying to find systems that have a very sharp, very strongly curved Solvis line. I want systems that I can dissolve a lot of my alloying elements at high temperatures, but very little at low temperatures. Okay. Okay. So the final thing about homogeneous nucleation is I want to talk about what is exactly the driving force for a nuclei to form, right? Okay, so we know that the overall driving force for the phase transformation, right? If I start with a alloy of this composition, X naught, Monday's lecture has not been uploaded. Shoot, thank you for reminding me of that. I'll get that in today's up right after this. If I start with an alloy of this composition, X naught, and I come down from the single phase region into the two phase region, right? I can draw my Gibbs free energy curves for both alpha and beta, and I know that I can reduce my overall free energy of the system by the common tangent construction by phase separating into alpha of this composition here and beta of this composition here. And my net reduction in free energy is delta G naught. Okay? That's my overall driving force to separate out the phase. Okay? But what is my driving force for nucleation? That's a little bit different. And the reason why it's different is because the nuclei that forms, the first nuclei that forms doesn't reduce this overall composition, right? Right? The nuclei is super duper tiny, right? So if we think about our chemical potentials at this point, right? At this alloy, at this temperature, at this composition, my chemical potential of A in alpha is down here. My chemical potential of B in alpha is up here. Right? If I take a tiny little bit of alpha, or if I take a tiny little bit out of this at the beta composition, right? Just the volume I need for a nucleus of size R star, right? The free energy of that composition, of that little block, right? It's still in the alpha crystal structure. I haven't actually rearranged it, right? So this, you can think of this as what's the free energy locally of my little cluster of size R star, right? It's going to be given by this chemical potential of B in alpha times the fraction of B in alpha times the chemical potential of the A in that cluster times the composition of A. So that puts me right here at point P. So inside my little cluster, my free energy is actually way up here. Right? This isn't the overall free energy of my system. This is the free energy just in that little cluster. Right? So this delta Gn here, this actually becomes my driving force for rearranging those atoms into the beta crystal structure and forming a stable nucleus, right? So the driving force for nucleation is actually much higher than the driving force for overall separation, right? If this was just the only reduction we got locally as well as globally, we would never actually go through the phase transformation, right? It's the fact that we get when we have a random fluctuation that brings things together, we're locally at this much higher energy state, but we can really drop it if we go from a cluster of alpha at this composition to a cluster of beta at this composition, right? That's an abstract idea, okay? Here's the same thing in words, right? But I think thinking about it in terms of the picture makes a bit more sense, right? If we're in alpha, right, and this is our overall composition, the local fluctuations are going to be on this line. Okay. Okay, so these are the idealized cases, right? The nucleation rate isn't going to be constant, right? If we quench down, we're going to go from, we don't have a perfect quench, right? We're going to have some cooling rate, right? The nucleation rate is initially going to be low, then gradually rise and then decrease again. Okay? This gradual rise comes about because of this, right? This gradual decrease, even if we hold at this peak, the gradual decrease is going to be that as we change our overall composition, we shift our average, as we grow beta, we're going to shift the composition of alpha this way, which means that our chemical potential of B in alpha and A in alpha are both, this slope is going to become less shallow. So as we nucleate more beta and beta grows, our driving force for the nucleation of further beta particles is going to be reduced. Right? So that means to think about this rigorously, we need to do everything in terms of time integral equations, which gets really nasty. Okay? So for what we want to do, we can think about things in terms of sort of this idealized picture. It gets us 95% of the way there. Right? We also assumed here that nuclei are spherical with the equilibrium composition and the structure of the beta phase. But in reality, nucleation is going to be dominated by whatever nucleus has the minimum activation barrier, right? We'll see this when we talk about heterogeneous nucleation, that sometimes we get special orientation relationships that develop, right? And so we get non-spherical particles because of that have a lower activation energy barrier. This also we'll see when we look at aluminum in just a little bit. that other metastable non-equilibrium phases form if they have a lower interfacial energy, right? GP zones and the other intermediate phases nucleate much easier because they have this smaller delta G star, even though they're not the thermodynamic energy minima. Okay. And we'll look at this for aluminum copper. Okay. So again, the important thing to realize here is that you basically know all this, right? This is just the solidification stuff with a slight twist, right? And so, all right. And you'll see that heterogeneous nucleation is also pretty much exactly the same thing. Okay. So nucleation in solids, like nucleation and solidification, is almost always heterogeneous. There are very few cases where we can overcome the energy barrier to nucleate homogeneously. Right? Most of those that do happen that way are metastable intermediate phases. They are not the stable thermodynamically stable phase. Right? So in liquids, we nucleated at mold walls or other solids or junk that's floating around in our liquid. In solids, where are we going to nucleate? Well, we can nucleate on if we have excess vacancies, dislocations, grain boundaries, stacking faults, or other special interfaces. Inclusions, meaning other phases that are there, right? So very often, like we'll see in aluminum, when we talk aluminum copper, when we talk about that, the thermodynamically stable phases nucleate heterogeneously from the intermediate phases and free surfaces. Okay. So all of these defects increase the free energy of the material inside, right? Obviously, dislocations come with a large strain and they have an entropy term. The vacancies have an entropy term. Grain boundaries and stacking faults are surface defects. Inclusions, there's an interfacial energy and a volumetric strain associated with inclusions a lot of the time, right? So all of these defects are high energy configurations. So if we can create a secondary phase there, and we do a phase transformation, and we're able, and by doing that, we eliminate that defect, right? Remember that we're doing, we have a diffusional phase transformation here, right? So we're moving atoms long range, right? So we can eliminate a dislocation or a region of grain boundary area. And in doing that, we're going to have some free energy. The free energy associated with that defect is going to be removed, right? It's going to be removed from our system, and therefore we can reduce our activation energy barrier, right? So now we just have what we had for homogeneous, our bulk free energy term, our strain term, our surface energy term, and now we have a reduction due to the defects that are being removed. Right? So let's take a look at nucleation at grain boundaries. Right? So in this case, if I've got a grain boundary here, I have a surface energy, the alpha alpha grain boundary. Right? And if I create a nucleus here, I'm going to be removing some area of alpha alpha and replacing it with some larger area of alpha beta, right? This is going to be preferred if the surface energy of alpha beta is lower than alpha alpha by essentially whatever this ratio of the areas are going to be, right? And so it's the same situation that we had except for solidification, except now instead of one spherical cap, we have a spherical cap on each side with an angle theta, and they're glued together, and this gives us this oblate ellipsoidal type shape, right? And so if we neglect misfit strain for a little bit, right, and we assume that this is a incoherent interface, and this grain boundary is also a general high angle grain boundary, and thus an incoherent internal interface, we are going to have a shape that's essentially just like this. It looks like an M&M, right? The contact angle is going to be given by the ratio of the interfacial areas. I mean, the interfacial energies, not interfacial areas, interfacial energies, right? And then the surface energy reduction is just the difference between the amount of energy AA alpha alpha interface destroyed plus the amount of alpha beta interface added. Okay. So again, this is completely analogous to solidification, right? We have a critical radius that looks the same. We have the ratio between, this should be homogeneous to heterogeneous is given by our factor S of theta, right? Our theta term is the same, okay? So high angle grain boundaries, where I have a big orientation mismatch across this, are very high energy. So they serve as potent nucleation sites. Low angle boundaries and special interfaces like twins are lower in energy, so they won't nucleate. There won't be as much nucleation happening on them. They're not as potent nucleation sites, right? So triple lines, right, are even higher energy, right? So they're even much more potent nucleation sites, right? And grain corners are even more. So this ratio, we get a big boost by potentially considering nucleation at triple points, triple lines, okay? So if we look at this ratio, right? If we think about, if we reduce delta G star by half, remember that our nucleation rate is exponential, right? It goes by our Boltzmann statistics. So a 50% reduction in delta G star is huge. So if we're in a regime where we have this, guess where all the precipitates are going to be? On grain boundaries. Right? There's no way you're going to get homogeneous nucleation when I've got a factor of 2 reduction. And that factor of 2 then goes into an exponential equation. Right? Which brings up an important point, is whatever is easiest to nucleate will. Right? It will be absurdly anything that gives you a small advantage in nucleation in delta G star is going to completely dominate in what you see when you look in the microstructure. Right? Right? So that's important. Right? Most of the time we don't see multiple types of nucleation happening. It's winner take all. Whatever one gives you a slight advantage in terms of energy is going to completely take off. Okay? So this is crucial because sometimes we have an orientation of beta where the lattice planes correspond well to certain sets of lattice planes in alpha. And in this case, we'll form a coherent interface here. Okay? Which means this interface is much lower energy than this one. Right? This situation here is going to reduce our driving force by that much more. I mean, reduce our activation barrier by that much more. And so this is going to preferentially happen. Right? The energy difference isn't super great, but because it goes into the Boltzmann statistics, we see this all the time. So if an orientation relationship like this is possible, it will happen virtually all the time. Almost every particle that we see will have this orientation relationship. 100%. Because the statistics, right? We're relying on random fluctuations, random thermally driven fluctuations to put our atoms in the correct configuration, right? The number of atoms is huge. The number of chances of, the number of times this happening is really, really large, right? 10 to the 11th per second in terms of vibrations, right? Somewhere around that order. So the fact that we're only nucleating at little discrete points essentially tells us that the right, it's the law of large numbers, right? The chance of a nuclei forming at any specific point is virtually zero. The chance of a nuclei happening somewhere is 1, right? It's like winning the lottery. The chance of me winning the lottery is 0. The chance of someone winning the lottery approaches 1. Right? And so now if you can imagine lottery a lottery where you could win with 6 numbers or 7 numbers, right? And one of them has a there's slightly fewer numbers to draw from, right? I don't, it's been so long since I played the lottery. I don't even know what the numbers are, right? How many numbers are there in Powerball are you selecting from? Right? I have no idea. Okay, but say you needed to select 6 from 50, right? Or 7 from 35. doing the multiplication right in my head, you should still have, or that 6 is still still favorable, right? Virtually all of the winners are going to come from that 6 category, right? Not the 7, right? You will have a small number, right? You'll have many, many more winners from the one that has a slightly smaller, slightly higher probability of occurrence, right? That's the thing about tails of a distribution, right? Okay, but anyway, if there is a slightly less energetically, a configuration that is slightly favorable energetically, that is what will happen. And that's the origin of these orientation relationships. This interface is slightly less energy, therefore a little bit easier to nucleate. So given the statistics of nucleation, it happens all the time, right? So this is very different than our expectation of the real world, right? Right. This is the statistics of extreme events, right? Okay, so what about nucleation on dislocation? Well, so the lattice distortion in the vicinity of a dislocation can assist nucleation, right? Around a dislocation, there's a large strain field. So if we have a delta GS that's compatible, right? If our volumetric strain is such that by nucleating at the dislocation, we reduce that strain energy, it's going to give us a boost. We can also reduce the energy because diffusion is faster along the dislocation. We have pipe diffusion, right? So by nucleating at a dislocation, we can increase the delta, we can get a bonus from our delta G of migration, okay? So dislocations don't really reduce the interfacial energy, but we get a boost from solute transport is easier and the strain effect, right? So generally what we see is secondary phases that are going to nucleate on dislocations usually are those that are would normally nucleate homogeneously, but they're going to nucleate much faster at the dislocation, right? A dislocation won't help us nucleate really large particles with a huge strain and a large interfacial energy. But they will really help us nucleate intermediate phases that have a lower energy, right? And the strain term and the little bit extra diffusion that we get means that everything is going to nucleate at a dislocation, right? Because of a small energy, that small energy bonus, right? Same thing with vacancies, except the energy of a vacancy is much lower than the energy of a dislocation, right? However, we do get increased diffusion rates when we have a large number of vacancies, right? So that means phases that would nucleate homogeneously, such as the GP zones in aluminum, are going to get a bump, right? They'll nucleate faster because of a large vacancy content, right?
Wait, I thought large vacancy helped heterogeneously.
The vacancy, yeah. So what it does is particles that would normally nucleate homogeneously, if there are a large vacancy concentration, they will nucleate faster. Whether you call it homogeneous homogeneous nucleation in the presence of vacancies, or heterogeneous nucleation is kind of a semantic thing, right? But having excess vacancies is not going to help you nucleate large, complex secondary phases. It will accelerate your rate of nucleation of things that grow homogeneously or nucleate homogeneously, right? Okay, so if we rank them from hardest to easiest, right? Homogeneous nucleation is obviously the hardest, then nucleation at vacancies, nucleation at dislocation, nucleation at stacking faults or low energy grain boundaries, nucleation at grain boundaries or other interphase boundaries, and then nucleation at free surfaces. Okay. The overall rate is also going to depend on the relative frequency of sites, right? So you'll see that we have a large dependence on the grain size, because the grain boundary surface area is dependent on what the grain size we have. If we have a smaller grain size, we have a lot more grain boundaries in our sample, right? And we also have to move our solute a lot less distance to the grain boundary. So our nucleation rate in a fine grained system is going to be much higher than nucleation rate in a large grain system because of the amount of grain boundary surface area that we have. Right? Okay, so that wraps it up for heterogeneous nucleation. Friday, we will go through the exam. And then Monday, I want to talk about examples in aluminum and steel. Okay, so everyone be safe. I try not to get stressed out too much about the continuing vote counting. I hope the candidate that everyone's preferred candidates wins. Right? Wouldn't that be great if that could magically happen? And we wouldn't have any strife. Right? And if your candidate doesn't win, I hope you find some really good protest songs to listen to, and that it continues to spur strong involvement from younger people in politics in this country. Right? I think that's the key to fixing a lot of our issues, is an awakening of the younger generation in the political spectrum, right? And it's interesting that the values that progressive young folks and conservative youth in this country has are significantly closer in terms of important ideas than old progressives and old liberal and old conservatives. So we'll stop there. Have a good one, everybody. And take care, stay safe, and be kind to each other.